So welcome everybody to the seminar today. And our speaker today is none other than Benjamin Doyon, who is so well known for his work on generalized hydrodynamics, of which he is one of the pioneers actually. So he will now tell us about how we can have a hydrodynamic theory of many body integrable systems today. So over to you, Benjamin.
Thank you. Yeah, it's a pleasure to be there to give this talk. And yeah, this is about this work that I've been doing in the past 4 or 5 years now about hydrodynamics of many body integrable systems. And basically it would be a bit of an overview. I mean, basically introduction to the main thing, the main theory, the main ideas. And if I have time, I'll tell you about some perhaps more recent results or kind of more advanced results within the theory. And please do not hesitate to stop me at any time to ask questions. I'd like the way I will present it is more from the conceptual side, not too technical, more from the conceptual side. So what are the concepts behind that and how it works and all that, with the idea that the general concepts can be applied in principle more generally and more widely. So if you understand the general concept, you can go perhaps even further. So the question based about that is the question of emergence. So basically, if you have a system with many particles or whatever degrees of freedom in interaction, it would be very difficult to describe each individual trajectories, of course, and not just difficult, but basically useless because it will not give you a lot of information. What you would like to have is a description about that takes into account the relevant degrees of freedom. And typical example, of course, is the molecules in the atmosphere that are, whose trajectories are virtually impossible to describe. But we don't need to describe these things. All we need to know is the general behavior of large groups of molecules and the equation that describe this general behavior. For instance, the equation that leads to the tornado. Right? So this is concept of the emergent universal macroscopic laws at large scales. For a reduced number of degrees of freedom, we don't need 10 to the 20-something trajectories. We just need much fewer quantities to describe what happens in a tornado, at least from large scales. Okay? So that's the idea. It's a very general idea. It can be applied to a great many situations. In fact, the typical type of emergent behaviors is what is described by quantum field theory. This is not in that slide now. Quantum field theory describes emergent fluctuations near critical points. And this is, again, this is a reduction of number of degrees of freedom to few fields, if you wish. It's quantum field theory. And it is universal in the sense that it doesn't matter what the macroscopics is. It can be very different and yet have the same emergent degrees of freedom with similar equations of motion and all that. Well, there's something similar that the same concept can be used to understand the equation of hydrodynamics, and this is what I'm going to be describing today and explain today. Okay? Now, hydrodynamics is not about critical point, but it's about the motion of many degrees of freedom in space-time, or motion in space, which trajectories in space-time. And what are the emergent degrees of freedom, the things that are actually relevant for large-scale observations? And what are their equations? This is the concept underneath hydrodynamics. Sorry for that. So, of course, this is a very old theory. Started probably earlier is one of those who first wrote basic equations of hydrodynamics. And there's, the basic equations are the so-called Navier-Stokes equations. Here are 2 equations written, part of Navier-Stokes equations. These are written here in 1 dimension. The first equation, that one, is really just conservation of mass. The second equation is something a bit more evolved, the bit where this is not there. And would be earlier equation, the bit where this is there. That is earlier equation, and the bit where you add another term, which I show now, would be Navier-Stokes equation. And these are the equations that describe what happens at large scales in fluids or gases, or whenever you have degrees of freedom moving in space-time. This is in 1D. Okay. Now, these are very simple equations, and they are supposed to be extremely universal. Okay, that's the main point. So, just to be a bit more precise, you think about systems in 1 dimension. I don't have to think about 1D. I could think about higher Ds, but for simplicity of presentation and also for relevance to integrable systems, I'm restricting myself to 1 dimension. Okay? So you're thinking about system in 1 dimension, so you have a lot of particles on the line. they have position xi and they move around. And you would like to see, to describe how they move. Of course, there's some equations for how they move, equations of motion, right? So dx dt is the momentum, well, which is essentially velocity at unit mass. Suppose you have particles of unit mass. And the PDT is controlled by the force, which can be obtained perhaps from a potential interaction potential between particles and perhaps an external potential giving an external force. So these are equations. In principle, you can put that on the computer and solve that. But if you have 10 to the 20 such equations, it's very difficult and it's virtually impossible. So you want to do some simplification. One possible simplification is to look at what happens macroscopically. So going from that microscopic picture to this macroscopic picture. And how you do that? Well, one kind of basic way is like looking from far away, right? In everyday experience, we don't see all the atoms, we see from far away. So what you can say is that, well, what we're going to see is not each individual particles, but perhaps some average of all the positions of particles within some length scale L. Okay? That is large compared to the atoms, but perhaps small compared to everyday objects, because your eye has quite a lot of precision. So L is large compared to certain distance scales, but small compared to other macroscopic distance scales. And that's some kind of average density. You can also calculate the average momentum density, where you average pi instead of the just number of particles. And you can call this rho times g, so introduce here some kind of velocity. And then if you do some little computation with appropriate approximation, as is done in our Lifshitz, just from these equations of motion, you can deduce global equations for these two quantities. Now, this is not a completely mathematical deduction. Of course, there's quite a few approximations in this, but the equations that you get are, well, conservation of mass or conservation of number of particles, which is this equation. And the other is conservation of momentum, or Euler equation, which involves a pressure term. The pressure is actually a non-trivial quantity to be calculated from essentially from the potential. And to calculate that explicitly, well, that depends on the model. That may be more or less complicated. And there can be also some external force if you have external potential. So these are basically the equations that are supposed to describe what happens when you coarse grain and go to large scale. So essentially in that limit. Okay. Now the question is, this derivation, if you look at how Lifshitz is extremely general derivation. So these equations look rather general. And they are a bit of a simplification. One can go a bit further and consider conservation of energy or entropy. You can also write something there. But still, they're supposed to be extremely general and applicable to a wide family of models. So basically, you reduce 10 to 20 trajectories or something like that to few equations. Here, just two equations for two functions in space-time. Okay? Now, this is very nice, but does it work? And what I want to come to here in the next few minutes is to say that it doesn't always work. Okay? So of course it works for the tornado in the US plains, and that, like in that pictures, if I were to write these equations in higher D in 3D and not in 1D. And they work pretty well, and they describe that very well, but they don't always work. And here I'm interested in one dimension. So indeed, let me think about a system which is a physical system, realized in experiment, which is essentially one-dimensional. And these are systems that have been done for a while now, since since the early 2000s. And they are systems composed of rubidium atoms, which are confined to be essentially in one dimension by appropriate, using appropriate construction, here using magnetic fields. And they are left then to move in this essentially one-dimensional tube controlled by magnetic field here, for instance. And they are put at very low temperatures so that the transverse degrees of freedom quantum mechanically are essentially never excited. So essentially it's a one-dimensional system. And then people can actually take pictures of these gas and analyze how they move in space-time. So this is a gas of particles. Typically in the experiment that I'm showing here, the Institut d'Optique led by Isabelle Bouchot, you have about 10,000 atoms, say, in this little tube. Okay. So it's a little tube, so you have kind of wires like that with magnetic field that confine the rubidium atoms to essentially a one-dimensional tube. And you have other wires that can be used to confine them in the longitudinal direction, but not, much less. So it's not too much confined that they cannot move at all. They can still move, but they are within some potential well. And for instance, you can put a potential well with two minima, or you'd have accumulation of particles along these two minima, or you can put various types of potential well. Okay, and this is a picture I mean, it's a reconstruction, but these dots, they are actually taken from experiment of more or less where the atoms are. They kind of lie essentially in one D and can move around. So this is a many-body system with trajectories. It's quantum. It's low temperature, but one can wonder how quantum it is now that, but it's still many-body system with quantum or classical trajectories that interact. Atoms interact with each other, and in principle, you may think that hydrodynamic works. Okay? Now, so what is this system? It's actually not too hard to describe explicitly. This system is, it's quantum mechanics, right? So there's a Hamiltonian, and it turns out the Hamiltonian is known. It's been known for quite some time for what these rubidium atoms should, how these rubidium atoms should interact. Is in some approximation, which is valid in most experimental situations, they interact just by a delta function potential. So basically, they don't see each other, and then when they're very near to each other, well, they kind of hit each other with some delta function potential, and there's some interaction strength G that can be deduced from the transverse potential that confine these atoms in 1D. So there's a relation between transverse potential and that G. And that is known from various analysis, and it's relatively well established. That is the right Hamiltonian. And here I put an external potential. And what we want to do, well, we could start with the potential that puts the atom into kind of two groups of higher densities at the minima of two potential. That would be your initial density matrix described by Hamiltonian H ini with this potential that has this shape. Okay? And then what you could do in order to make things move around, to see if you have hydrodynamics, to see the emergent dynamical degrees of freedom, you could just suddenly change the potential. People often call this a quench. Well, it doesn't matter how it's called. You just suddenly change the magnetic field. You change, if I go back here, you change this magnetic field in such a way that this potential changes its shape suddenly. And then, of course, the atoms are no longer at equilibrium, at thermal equilibrium in the original potential, so they start moving around. They feel a force of this external potential. So for instance, you can change it to 0. So you have no longer confinement of these atoms, and then they start moving here, for instance, in the opposite direction. Okay? And then you can wonder how will these two density of atoms move around. And if you, of course, I should say this is a very well-defined quantum mechanical problem. You just have to solve this quantum mechanical problem, but it is difficult to solve because it's a complicated problem. There's interaction, and there's non-inhomogeneity, there's potential, there's a lot of things happening. In principle, you can put that on the computer. And it turns out that if you don't put this potential there, then that Hamiltonian, just this bit of the Hamiltonian, is actually an integrable system. And of course, that connects with what I'm going to say later. But that being integrable, that means you can construct exactly its eigenvalues by beta and z. There's an efficient way of constructing all the eigenvalues and the eigenvectors. And then you could use this basis and try to add this term which breaks integrability, and then see if you describe the evolution. Fortunately, this technique is still quite limited. You can go to about 50 particles or so. It's quite good, but it's quite limited. You cannot really describe the full 10,000 particles in interaction and see what emerges at large time. So it's good, but it's still a bit limited. And it's very computationally intensive. You'd like to have something that describes what happened at large scale, so a simpler equation. So you could try to do the hydrodynamics, right? So this equation, you could say, well, why don't I use these equations to describe what's happening? It turns out that the pressure term is known exactly because the model is integrable. To vary the pressure, people have thought about that. All you need actually is eigenvalues, and you have eigenvalues can vary the pressure. Well, essentially, yeah. So, okay, so you can do that and see what happens and compare with the experiment. This is an experiment, right? It turns out that if you do that, so this is the initial curve. The density is accumulated on two minima. It's not exactly symmetric because it's very hard to adjust these magnetic field very precisely, but more or less is that. And then you evolve it, and you see that there is the weakly curve, which is the experimental result, and then there's the dotted curve, which is the result from solving the hydrodynamic equation, the equation that I showed you at the beginning. And you see that it works very, very badly. It doesn't work at all. Okay? So these equations that are supposed to be very universal, derived in analogies with some kind of universal argument, don't really work. Now, there are many reasons why this may not work. Maybe because this is a low temperature quantum system, there's quantum effect, or maybe there's something, this is an experimental result. Okay? But it turns out that we have another. Yeah, go ahead. Yes.
So is it important that whether they're bosons or fermions here, or whether this?
So that's a good question. So here they are bosons, except if with the delta function interaction and this being in 1D, this can also be described as a fermionic system. So it can be, so the system, you can write the wave function in a symmetrized fashion, or you can anti-symmetrize it. And you have then a different Hamiltonian that will describe what happened for the fermions. So this has two descriptions, one in terms of fermionic, one in terms of bosonic degrees of freedom. It's possible to do that in 1D because 1D is very special. You can symmetrize or anti-symmetrize. It's a bit of a construction. And so in fact, it doesn't appear that this to be particularly important that it be boson or fermions. In fact, there are also other systems where the fundamental particles, the rubidium atoms, are in different levels now, and they actually become fermionic, like half spin, right? And then you have similar interactions now and you can see that similar effects as well. Okay, so bosonic or fermionic is not that important. Does not appear to be the main principle behind this working on that. I understand that the analysis, of course, is classical, particles and all that, and naturally we boson all this. But the general principles of hydrodynamics would tell you, well, it should work also with fermions with a different pressure term. The pressure term might have the fermionic statistics within it, and yet here it still does not work. Okay. So it doesn't appear to be the main thing that it be fermionic or bosonic. Yeah. So somehow it seems not to work, but I mean, I should say, of course, there's many reasons why it might not work. There's a lot of things going on. But perhaps the main thing that I want to say is that, well, there is a theory, is the theory of generalized hydrodynamics, where you see kind of the fuller curve there. That full curve agrees very, very well with this experiment. So it looks like this theory, which accounts for integrability of the non-perturbed system. So that system is integrable. So apparently accounting for integrability of that bit of the system helps you agree with the results. Now, actually, people have analyzed this experiment result also later on and tried different theories. In fact, there are other ways of correcting the Hadro equation to make things that seem to match kind of relatively well with this, but they never match as well as GHD. And in the end, there are other numerical results and experiments that show you that accounting for integrability seems to be a very crucial thing to do before accounting for anything else. Okay. So then the next thing, that's what I kind of want to convince you that we should account for integrability. Any questions about this? Other question? So before I go there, in fact, I think this is important. Oh, yeah, I should just mention, of course, this describe our experiment. Oh, yeah, question?
Can I ask a question?
Yeah.
So, I mean, integrable system, there are infinite number of conservation laws.
Yeah.
Are you going to sit and consider all infinite of them, or
exactly.
What is the important subset?
Yeah, exactly. So this is, thanks. So this is, of course, the crucial point that I was telling you about conservation of mass and momentum and all that. Of course, there are infinitely many conservation laws. So you have to account for infinitely many of them. But then you say, well, I mean, maybe some are more important, and how do you account for infinitely many? And that's the whole thing of GHG, that you have to account for it in the good enough way. And so I'd like to explain how one gets there. It is not just writing infinitely many equations. That just wouldn't work. You have to do this cleverly enough. And the way that we do, so I'm going to explain that. Yeah. So I just wanted to mention that our experiments was not, of course, the first one. Perhaps the most important experiment is the one done by Kinoshita, Wenger, and Weiss in 2006, where they there pointed out that probably one should account for integrability in order to describe these large-scale motion of cold atoms confined to 1D. They had an experiment where they would see clouds of atoms colliding and not thermalizing this. Okay, well, there's something about integrability. And that sparked a huge amount of research about generalized thermalization, GGEs, and eventually that led to our work on GHD, and then eventually we could explain this experiment using GHD.
Can I ask one more question?
Yeah, go ahead.
Yeah, is dimensionality important as well?
Yeah, so this is also a question that is often asked. So in the whole thing that's been developed in now, dimensionality is crucial in the sense that we are dealing with one-dimensional integrable systems and the particular structure of one-dimensional integrable systems. Now, there are integrable systems in higher D, and I don't know enough of the theory right now to see if the structure that we are using actually can be used in higher D as well. And there's a lot of properties of 1D that we are using. Nevertheless, the general principles that I want to get through now, they are very general. They are not confined to 1D. And I believe there is an extension of that to higher D. There's a lot of possible extensions of hydrodynamics using the general principle that going beyond GHD has developed till now. Okay. Other questions? So basically, I'd like to go kind of back to basics about hydrodynamics. What is hydrodynamics and how do we modify it to account for integrability? So that's the main part. I mean, I think it's important conceptually. So what's hydrodynamics? Well, you look at the system here. It's a 2D picture just for clarity, but it doesn't have to be 2D. Look at your system and it moves in space-time. There's non-trivial dynamics and all that. But what's the idea of hydrodynamics is that if you look in mesoscopic, so this is macroscopic. If you look in mesoscopic cells, which are small compared to your macroscopic point of view, but very large compared to the atoms. So for instance, a little drop of water, a very small thing in your bath. You look at that. Well, it should look more or less homogeneous and stationary. So on short times and on short distances, the state that is there, the particles will move around, of course. But the state that is there probably will have reached some kind of equilibrium, and it will not move. The state will not change too much. Particles move a lot, but the state will not change too much. So it's a local thermodynamic state, sometimes called local thermodynamic equilibrium, although it's not quite the right terminology. So it is homogeneous in a statistical sense and stationary in a statistical sense. And but if you look at different places, it will be a different homogeneous stationary state. So different states everywhere, and you have an emergent dynamics on these states that you will find at different points in space-time. That's hydrodynamics. It's the dynamics on emergent thermodynamic states. Okay? Emergent thermodynamic states that describe the state of fluid cells, so at the mesoscopic scale, which is the scale between microscopic and macroscopic. And microscopically, of course, then you see all these trajectories, but we don't want to go into that. There's no point trying to describe trajectories. Okay? And the whole point about hydrodynamics is to find out what are all these thermodynamic states that describe local fluid cells, and then to put the dynamics on that. And this is, of course, where integrable systems is different from non-integrable conventional systems, because the set of thermodynamic states is different, is larger, okay? And that's what I want to explain. Okay? Now, so that means there are two steps in this construction of hydrodynamics: understanding relaxation in isolated systems. So basically here you say, well, a lot of things happen, but after some time, this will relax to some thermodynamic state. The time is relatively short compared to macroscopic time, should be short compared to macroscopic time, but still large compared to microscopic time, like collision time, the time for collision to happen between particles, for instance. Okay. So some kind of relaxation, and we want to know, a system will relax to what in general? Describe these states. And then when we have these states, we use the hydro assumption, which is the assumption that you have these states everywhere, separately everywhere on fluid cells in space-time, and then extract dynamics from that. Now let me just then consider here the first point, relaxation. And this is, okay, we don't want to describe relaxation in fluid cells. Fluid cells are surrounded by a lot of things, but you can think of that as an isolated system, but very, very large. So let's think for simplicity, an isolated system, we don't want to have to describe an external bath, because then you'd put additional information in the bath. We don't want to have additional information. It's just purely the system itself that self-thermalizes and that relaxes locally. So let's just think of a system itself, very large. We want it very large because we want to describe what's happening in the mesoscopic cell, something that's large compared to the microscopic degrees of freedom. And let's look at, let's consider it to be homogeneous. So the cell is essentially homogeneous, okay. And now let's look what happened if we let the system relax. So suppose it is not initially in some stationary state. It's some state which is complicated, which is not stationary, which a combination of many eigenstates with different energies, for instance, like a lot of them. So, and we have some initial state and we let it relax after a long time and we look what happens. Now, since we want to describe fluid cells, we better look locally in this big system, what will happen? So reduce density matrix, if you wish. Okay. So what will happen? Well, this is a relatively complicated question. So you can start with some Your initial state might be a pure state or a mixed state, it may be classical or quantum, and then you let it evolve for a large time. This is kind of a quantum point of view, and see what happened locally and what it may be. Now, the idea of hydrodynamics that locally, or the idea of relaxation is locally, it should be a Gibbs state or something like that. That's what Gibbs tell us, right? That things should write to Gibbs state. But let's be a bit more precise about what this may be. So before that, I want to point out that there is a relatively precise formulation of this question. The formulation is what are the possible, the formulation is as follows. So what we want to consider are not all possible observable everywhere, but just local observables, because we want to look at fluid cells. So there's a notion of locality in an extensive system, which is absolutely crucial. And mathematically, this is most efficiently addressed using the notion of algebra of observables, usually from a C-star algebra. It doesn't matter too much of detail, but it's an algebra of observables. So you look at all the possible observables that act locally on some space-time. It doesn't have to be local at a point, but at least on some small region. Okay. So for instance, the bounded observable on some subset, L2 space acting on some subset of the full system. And you look at all these possible observables. You take a large L limit, but essentially every observable is local in some region. And you look at the possible set of states. I want to know what's happening at large time, so I want to have states. So what is a state? It's best to take a complete general definition. It's the positive linear functional that tells you for every observable what its average is. So you're looking for appropriate positive linear functional. So forget about pure state or mixed state. Now that this is an infinite system. And the distinction between pure state and mixed state, especially when you take reduced symmetrics, is not very strong. So what you want is really linear functional on set of observables. There's a time evolution, of course, on these observables. There's also space translation. And you start with some initial state, which is invariant of the space translation. That's your assumption of homogeneity. And then you want to know what happened at large time. And a typical thing to do is to do the time averaging. And there's a lot of people who have studied this kind of averaging in quantum systems, starting with von Neumann. There's something called the quantum ergodic theorem, where time averaging, or even actually a bit more, is related to macrocanonical observables. But so that's the question. Now, yeah.
Benjamin, can I ask a question here? So normally in the formulation of hydrodynamics, we also have some sort of a notion of an entropy that through the relaxation. Is there something analogous one can in the space of algebra in this natural?
It goes a bit further, but there is this is actually a very interesting question, and people have asked about: is there a notion of an observable that gives you the entropy? There kind of is, but it's a bit state dependent. So there is a way of writing an entropy in terms of local observables, but it's not a complete. It's a state dependent way. For a given state, there's an observable local observable that tells you what the entropy is, or local entropy, and then you can ask about how this entropy changes on the hydro, and increases and gets to a maximal and all that. Yes. So there is a way. Let me just maybe continue a bit and tell you a bit what that way is. there's a way. I need to say a bit more about it. But yeah, there is a way. So there is a notion of entropy and its increase and maximizing it, and that leading to the Euler equations. But before that, so there are these observable in principle. We want to ask that. So a lot of the work has been done before understanding the thermalization in integrable systems was making assumption actually on the dynamics. The assumption is essentially that it be chaotic. There is one assumption that people do starting from von Neumann actually, that energy differences should be non-degenerate in finite but large systems. So that's an assumption which you can do, where you can deduce something about this kind of large averages, something very general, but it's not sufficient for us because we have integrable systems that break a lot of these assumptions. So there should be some general principle. Okay? And that's what I want to so what are the possible states in general? Okay. Well, turns out that, so that it comes in 2 points. I know people often think in terms of entropy, but I'm going to come to that. Actually, the 2 points are, I think, a bit more fundamental than that. Okay. So what are the states that can occur? Well, certainly, if you do the time averaging, or if you take large time, if the large time limit exists, the state that you get should be stationary. So whatever it is, maximal entropy or not, it should be stationary. So it should be a stationary state. It's also homogeneous because we start with homogeneous. And also the other condition that about the state that you obtain is that, well, if you have some kind of relaxation, probably the state that you will get will be such that when you observe in one point in space and some other point in space, your observations are very much independent from each other. If the points in space are very far separated, so there should be some clustering. So if you look, so this is stationarity. If you look at two observable on two different regions and take the regions very far from each other, the average should cluster into product of average. Now this is very non-trivial, and it is nobody knows how to show or what type of initial state will give you at large time clustering states. This is non-trivial. This kind of it's not really proven, and it's not trivial. But physically, it's what should happen, and this is essentially sufficient to characterize a set of states. So essentially, what you're looking at is the manifold of all homogeneous stationary clustering states. These are the relaxed states. These are the thermodynamic states that people think about, and these should be from your question, and this should be the state that have maximized entropy in some way. Okay, so this is the basic notion. The states that we want are homogeneous stationary clustering states. Okay, and clustering is actually crucial. Yeah.
Does ergodicity follow from these 2 points? I mean, which is like time average equal to spatial average?
So this is a very interesting question. Does ergodicity follow from that? And until recently, as far as I understand, there were no results about this. So this is really a crucial question, I think. So basically, clustering in space, does it mean that you will have ergodicity that the time average would come back to the ensemble average? But we have results with my student recently that show some weak version of ergodicity and how it actually follows from that. So yes, now we can say it follows in a weak form from this. And the fact that it follows from this, the fact that you have ergodicity is actually at the basis of the emergence of hydrodynamics. But this is kind of more recent result. Maybe if you ask me at the end, I can tell you a bit more about it. But yeah, but that's a good, excellent question. Thank you. So, but the physical principle is okay. We would like to have these states somehow. These should be the right states, and now we understand ergodicity follows from that. These states have been studied a lot in the context of quantum statistical mechanics in the 60s and 70s. They're always thought of as being the right state for describing thermalization. But not a lot in the context of integrable systems. And this is where comes the second point, that it is believed, again, not proven, but there's a lot of indication that clustering and connecting to this ergodicity is actually related to the fact that these states can be described using extensive conserved quantities. So certainly if they are homogeneous stationary state, something of the form exponential of a sum of all quantities which are conserved by the dynamics will be fine. That's homogeneous and stationary. And anything that's conserved that has a, that is homogeneous, say integration over x of some density will be fine. But more than that, these exponential of things which are integration over space of local density are actually clustering. So these are the extensive conserved quantities, and these give rise to clustering state. Note that I could take any function, not just the exponential, any function of such extensive conserved quantity that's still homogeneous and stationary, but not necessarily clustering. So clustering, separation of, the fact that different regions are essentially independent, tells you that you must have exponential of extensive conserved quantity. So that's the Gibbs form. So clustering gives you the Gibbs form of state. And then from this, you could think about entropy. There's a notion of entropy, and the basic notion of entropy is this. So basically beta I, the average of the QI, minus the free energy, that's your entropy density, minus specific free energy is your entropy density. And so basically this times that, minus free energy, you need to relate that. Well, so from this you can extract some kind of local observable that will give you the entropy density, but it is state dependent. Okay? And it is based on the fact that you must have a Gibbs form. And this Gibbs form is essentially a maximization of entropy. Right? So you maximize entropy, but without the conserved quantity being taken into account. So the question now is, what are all the extensive conserved quantities? And of course, this is where we connect with integrability, because you have a lot of these things. But it is crucial that they be extensive, I should say. Yeah, the question?
If it is of the Gibbs form, it is quite obvious. What should naturally follow is, for example, you take a correlation function like in your previous slide. it should only differ. It will have a difference between translation and variance. But you are talking of an extra factorization here. Of course, in the limit, a prime goes to infinity, right? Only in this limit.
Yes.
So basically, it means that this should be that the beta should be some kind of a scale that should tell you about what distance you should take, right?
Correct. Yes. Correct. Exactly. So precisely the betas give you tells you about the correlation length. Correlation length would be beta dependent. So beta gives you the scale in some way, but it's in some complicated way in general. But in some way, it does give you, indeed. And there's also another thing that can give you the scale. So these constant quantities have a local density, but the local density is not necessarily supported on a single point. It might be supported on a whole region, finite region. And that also provides a scale of correlation. Of course, if this region is large, then you have, correlation don't decay as much. You need to go beyond the region. So the scale of correlation that's produced by the betas and by the length associated with the local densities. Other questions? Yeah. So extensivity is crucial. In fact, this was an important point in the understanding of thermalization in integrable systems. The understanding that you need to consider all the extensive conserved charge. And then people came up with kind of a proper notion of what an extensive conserved charge is. A lot of work by Posen and Ilievsky originally, and some of my work kind of clarified a bit the structure of this. So essentially, what is an extensive conserved charge? Well, you can write this as an integration over density, but you cannot always write it like that. In fact, a conserved charge is defined in kind of a bit more abstract way. It's some limits, some weak limits. It's a limit of operators supported on larger and larger and larger regions, with the condition that the limit exists, if you take the connected correlation function with any other observable. And with the condition of extensivity, that if you take the connected correlation function of a square of that quantity, I should put absolute value, should not grow more than, I don't need to put absolute value, it's real, but okay, should not grow more than the length of this region. And if you look at this, the square of that will have two integrals, but if the state is clustering, only one integral will remain where you have non-trivial things to sum over that will scale like the length of the interval. So this is the extensivity. And then you should have homogeneity, stationarity. And it turns out that the set of such weak limits form a Hilbert space. It's a complete space. And this is the space which describes geometrically the tangent in the manifold of all these clustering homogeneous and stationary states. So this is the geometric description of the set of states. And then what you want to do is put hydrodynamics on this set of states. Yeah.
What does connected mean? I'm sorry.
So so connected is this thing that you just, was the fact that you here that you subtract the product of observable, so that this goes to zero, at large distances.
Okay.
The connected.
It is what we call the connected correlation function.
Yes. Exactly. Yeah. So you look at the cumulant essentially, second cumulant. So basically the tangent is described by inserting this extensive charge inside connected correlation function, and effectively you cannot always describe these charges as integration of local densities. It's a complete space, and you have to have kind of a description of this complete space. Anyway, this is a bit perhaps abstract, but this is the general notion behind hydrodynamics. And then what you want to do is just put essentially arbitrary effective inverse temperatures, these betas, at different points, and put and do this hydrodynamic approximation where every local observable evolved from some initial state that is in homogeneous null that at large enough time will be described by locally some of these betas that now depend on X and T. So you have local fluid cells which have maximized entropy with respect to our conserved charges. Now you want to put the dynamics on that, but then this is relatively simple to put the dynamics on that. You just have to write your conserved charge again, but formally you write it as integration over density. But this is fine general. And then since this is conserved, there should be a conservation law. So there should be a current associated with it, which is also local. And then the idea is that the conservation law at the microscopic level also holds at the macroscopic level. You have a macroscopic conservation laws. And this is just using the hydrodynamic approximation and you can actually derive this hydro equation by rewriting this differential conservation in integral form, and then using the hydro approximation everywhere on the integral. And you get the integral form at the macroscopic scale if your integral is not over macroscopic scale, which you can rewrite in terms of microscopic, well, this is now mesoscopic equation essentially. So what you're saying is that the averages of densities and currents are related by this equation, but the averages of density and currents are both controlled by the betas. So you have an equation for the betas, and that's the hydrodynamic equation. That's it. This is hydrodynamics, completely generated. The main ingredient is to find this set of states, all the betas, and then calculate the density and the currents within that set of state, and then write the equation. And then you have an equation you have a hydro equation. If you just concentrate, oh yeah, go ahead.
So in the case of normal hydrodynamics, suppose you have many conserved quantities like energy, momentum, charge, they can have their own individual velocities.
Yes.
And so not only the betas, we also have, like, if you have so many conserved quantities, we can also have different velocities, right? And
yes, so let me just point to that. Actually, I think this comes to my second point. Excellent. So the betas, so in the standard case, suppose you have particle momentum and energy being conserved. Okay, just in non-relativistic. Relativistic, you're going to have momentum and energy. That's it, right? So and you 1D, so it's just that. But suppose you have these three. Well, suppose you have the particle density, the momentum density, which I can write as 0, and then there may be another one, Q2, which is the energy density, say H. Okay, so I will have three of them. I'll have three equations there. And that's it. These are the hydro equations. Now you say there's velocity. Well, yeah, you can write the equations. Okay, first of all, if you write momentum density, this one, you want to write something like e to the, so there's a, you can write like that. Beta, there's a particle number. Sorry, I would like to write the Hamiltonian, of course. There's a chemical potential with the particle number. And then there's perhaps a boost nu with the momentum. And that boost kind of tells you about the local velocity of your fluid cell in standard hydrodynamics. So there is the velocity, right? There's a boost associated with the momentum, right? That's kind of a natural velocity. So this is what, it's more like a Galilean boost, okay? You can also associate velocity more fundamentally to this equation by writing them in the quasi-linear form. So you know that both the Q's and the J's are related to the beta, are fixed by the beta. But you can invert the equation from betas to Q's and actually write the currents in terms of density. So instead of using temperature, chemical potential, and boost, you can use energy density, momentum density, and particle density as your fundamental degrees of freedom. And write the currents in terms of these. And then that becomes the equation becomes so-called quasi-linear form, where it appears linearly in derivative, but this flux Jacobian, the Jacobian of currents to densities, is a non-trivial function of the densities, non-linear in general. And the eigenvalues of the flux Jacobians are the hydrodynamic velocities. So like the sound velocities, propagating of sound in ordinary hydro, this is an eigenvalue of the flux Jacobian. Like there are two eigenvalues, plus or minus sound velocity, and there's another one which is equal to the boost velocity, and that's just the velocity for the heat mode. Okay, so these are the natural velocities that emerge from the hydrodynamics. Does that answer your question?
Yeah, that does answer. I think I get the answer now. So I think, but I want to confirm with you if I've understood it correctly. So if you look at, for example, Navier-Stokes hydrodynamics, you do not assume that the things are always in local equilibrium like this.
Yes, correct.
And then
yes.
If you are in equilibrium, then of course all the charges have to have the same velocity because it's only one equilibrium frame, and all charges have moved. And then when you write departures from this local equilibrium form, then you have to worry about these different velocities and choose a proper frame and all this. But
yes.
So is that you're always in this local form, right?
Yes. So I'm always in the local form. So you have to be a bit careful here. So this is kind of very, very general in a sense. Okay. And what you have in mind is the local equilibrium. Because in the local equilibrium, you can go to the frame where there's no overall velocity. That's the boost. I mean, you can go to the frame where the boost is 0, you can put the boost there. So if you just look at that there's no overall velocity, right? So things don't move overall. But then, of course, this is just assuming that you reach local equilibrium. Of course, this is kind of under the simplification. So two things I want to say. Navier-Stokes will correspond to additional term, something like maybe zeta, and then you have a dx squared q or something like that. Additional term, where you break the local thermodynamic equilibrium. Okay? And to describe that, you need a bit more theory. And I don't want to go into that because already for integrable system, this bit is kind of sufficient to describe a lot. So it's really the simplest part of hydrodynamics, where you assume kind of local equilibrium. The second point I want to make is that this notion of local equilibrium is not quite the right one. It is the right one for conventional hydro, but not for integrable system. In integrable system, you can have more velocities even after assuming kind of local relaxation. In the ordinary case, because you just have one possible boost, normally you just have one possible velocity, and then you can put it to 0 by boosting, and then you have that. But in more general cases, you may still have many velocities, even after relaxation, local relaxation. So there may still not be a notion of a velocity being 0. Yeah, but here in the standard case there is. So there's this velocity, and you can boost and put it to 0. You have local equilibrium. But that's the standard case, and that's, you see, it's important to take the general point of view to go beyond the standard case, essentially. The questions?
Thank you. Okay.
So sorry, I think I'm talking a lot, but I think I'll get to the integrable system. I just want to say, yeah, there's no need to assume the system to be chaotic for this whole thing to work. You see, the main thing is to determine the set of states. Doesn't matter what the system can be very special, very constrained, a lot of conserved quantity. Then maybe you have a large space of possible relaxed state, and maybe then the equation is not useful, maybe it's useful. But the point is that there is a space of state describing relaxation. That's what you need to discover and to use. And that will apply then to every is a little big word, but a lot of local interaction system of many types. Quantum, classical, doesn't matter. For integrable system, let me give you a simple example. And the example kind of describes essentially all integrable systems, although it's extremely simple. The example is particles that interact with each other and that interact in a very simple fashion. They essentially, when they collide with each other, they just exchange their momentum. So elastic collision. So a bit like free particles, except that they collide, exchange their momentum. But the particles have a length, just to make it a bit less trivial, they have a length A. Okay? So these are rods. It's called the hard rod gas. Okay? So it's a gas of particles that kind of exchange momentum when they collide and go about their free trajectories otherwise, and they have a finite length. Now, there is a lot of extensive conserved quantities in this model because all the velocities are conserved, obviously. When they collide, they exchange velocity. So if you start with a set of velocities, over time, you always have the same set of velocities. So you can write explicitly in this case, these extensive conserved charges for every velocity. I call this theta. It comes from QFT. Theta is a rapidity, but it doesn't matter. So here's the velocity. Okay. So for every theta, there is a conserved charge. You can write it as integration of the local density. We just look if there is a particle at x, and if there is, it looks if its momentum, which is the same as velocity at unit mass, is equal to theta. So this is kind of of course, it's a density with respect to momentum in space, okay, or respect to velocity in space. So it's a phase space density, and that is conserved throughout time. And so you can write then your phase space measure for your conserve for your states. You can write it as exponential beta I qi, but since there's a continuum of theta, instead of the betas, instead of the beta i's, what you have is the w of theta, called the w now, so like beta of theta. So you have a continuous sum of all these q of theta that you put in the exponential. Of course, that can be rewritten simply. You can do the integral, and essentially you just put a weight on every momentum given by a function w. So you have a function that describes the whole set of states. So this is you have a continuum of states. Like it's a very large continuum. It's described by a function. You need a function, not set of betas, so not finite dimensional, but infinite dimensional. Now, this is a situation in integrable system. You have an infinite dimensional set of homogeneous stationary clustering states. So these Gibbs states now form this is an infinite dimensional manifold. And then you need to describe an evolution equation on this infinite dimensional manifold. So let me just say a bit more how in integrable system it works in the Lieb-Niger model, which is integrable. Well, you cannot describe explicitly all these q theta, but the basic idea is the idea of scattering. So instead of looking at the particles where they are and the velocities, you cannot do that. It's too complicated. But what you can do is look at what happens when you take your gas and let it expand, say, for a long time. And then you see freely propagating particles. This is the QFT concept of asymptotic states. And they have a set of momenta. And this set of momenta in integrable system is conserved by the dynamics. So essentially, if you start with an in state without this set of momenta and let them collide, after in the out state, you have the same set of momenta. And more than that, in fact, the scattering matrix can always be written as a product of two-body scattering matrices, as if all these processes happen in a separate fashion. It's very similar to the hard rods. If you look at the hard rod, the collisions would happen two-body by two-body. Always, I mean, almost surely, right? It's extremely unlikely that you have three at the same time. Actually, the model doesn't even tell you what to do if this happens. You just exchange momenta. So two-body by two-body. So it separates into two-body scattering, and the asymptotic momenta are the same before and after. So these are the properties that we need, it turns out, to describe everything. And these are properties that are true for a large class of integral models, quantum field theory, or not, or kind of particle models, quantum chain, Bethe-Ansatz, integral models, and all that. They always have that structure. These thetas in Bethe-Ansatz are essentially the Bethe roots. The roots tell you about the asymptotic particles. In any case, so this is the QFT concept, really. And so in the end, you can think about asymptotic state characterized by these thetas and Q thetas acting on this asymptotic state just by counting how many particles you have of these thetas. And these are the Q that allow you to describe the state that have relaxed. So essentially, the set of all Qs forms some kind of scattering basis for the big Hilbert space of extensive conserved quantities. It's a L2 Hilbert space. Doesn't matter too much these details. For instance, the energy can be written as an integration over these Qs with, appropriate one particle eigenvalue. In Galilean system, is theta squared over 2. In integral model, in a relativistic model, cos theta. Okay. So these are all the Qs, and then you just write your density matrix in that form, and that's it. It's a bit of a formal way of writing it, but it's kind of a useful way. So this tells you that this is the set of possible states that describe your hydrodynamics. So formally, then you can write your conserved densities as function of these W's, and there's something called the thermodynamic Bethe-Ansatz, so TBA, that allows you to exactly calculate that. Given the betas, which are now really the W's, you can calculate the Q thetas. So this is thermodynamics. It's like, this is your thermodynamic state, so you know that. Then all you have to do is write the equation of motion for your hydrodynamics. Okay? dtq plus dxj equals 0. For a continuum of theta, for all theta in real. So you have a continuum equation. Any question for that till now? So this was actually, until there, this was pretty well known by many people. What was not known actually in the context of integrability was how to calculate the currents for such conserved quantities that are defined by acting on the asymptotic state by just measuring the thetas at a given theta I. I mean, because one doesn't even know how to write these currents, especially, well, one didn't know. Nowadays, people know a bit better how to write that, but one didn't know how to write these currents, especially microscopically. And so this was kind of a difficult problem, let's say. But that's what we managed to do, we and another team, two teams separately managed to do, to write explicitly these currents in terms of the densities. So if I write the densities at some function rho of theta, this is the density of Bethe roots in the Bethe-Ansatz formulation, where the current is just obtained by multiplying by a certain velocity. And then there was, one of you was asking, Ayano Suresh was asking about the velocities. Well, here, because there's a continuum of conserved quantities, there's actually always a continuum of velocities. There isn't a unique velocity. You cannot put it to 0 anymore. There's always a continuum of velocity. So you cannot really describe this as being equilibrium state, but still it's relaxed state. It has relaxed. So it has maximized entropy with respect to all conserved quantities. And these velocities, they are non-trivial functions of the rho's, functionals, the facts of the rho, and they are obtained by solving a linear integral equation. Now, the linear integral equation knows about the density of all these conserved quantities, and also know about the dynamics itself, the interaction, and it knows it via this quantity, which tells you about the two-body scattering, essentially the derivative of the log of the two-body scattering phase. In general, there's a matrix now that is a bit more complication, but in the simplest case, like Lieb-Vinegar, this is it, right? This phi is known exactly in Lieb-Vinegar. So in Lieb-Vinegar, it takes the form C over C square, or maybe G over G square plus theta minus alpha square. So it's a very simple function. You just have to put it there, and this equation principle can be solved. And now this equation has to be solved numerically, and in the end, the equation that you get like that, you have to solve numerically. It becomes a non-trivial integral differential equation. So this expression has been derived in various ways. We derived it in quantum field theory using crossing symmetry. Then it was derived using Bethe-Ansatz and using various other ways, also in classical models, like other models. There are now quite general and strong proofs using integrable quantum investigating method, essentially. So the Bethe-Ansatz formulation. But let me just before I go there.
Benjamin, I just want to know about what this notation. What is rho p at? What does this p stands for in this?
Yes, yeah, this is notation. Sorry about that. So this is relatively standard notation. It stands for particle, quasi-particles. So this
okay.
there are different rows in the bit. There's a density of state, density of particle, density of holes. You imagine that you have quantum numbers that can be filled in or not, like for fermionic systems. And this row tells you of the density of quantum numbers that have been filled in, so particles. Then there's another one that tells you the quantity of those that are not filled in, holes, and then the notion of state, density of possible quantum number with respect to real momenta, density of state. This is a very fermionic Bethe-Ansatz point of view, but in fact, the whole Bethe-Ansatz structure at the thermodynamic level holds even for classical system. It's a very, very general structure, and these equations are also very general structure. Yeah, so maybe I pass. Sorry, I'm getting a bit late, but so the equations that we want to write then are for now space-time dependent states. Now the states are described by this one function, this rho of theta, rho p of theta, and that function describes kind of essentially all the inverse temperature, if you wish. And now we write dtq plus dxj equals 0. Our j is some velocity times rho. I come back to that if you allow me. And then we write this equation, and that becomes the integral differential equation of generalized hydrodynamics. That what replaces the usual equation of hydrodynamics. And you see that there are infinitely many velocities. There's a big spectrum of possible sound velocities, so to speak, right? There's generalized sound velocities. They actually form a continuum. And that means that in GHD, you have a lot of very different phenomena. When you speak in an integrable model, integrable gas, your sound does not propagate nicely linearly, in some direction. It propagates at all possible velocities. So you would not hear some, beep. You would hear some elongated beep that's coming at all possible velocities. And this is actually the reason why you have, sorry, I passed things a bit fast, why you have this structure in the experiment. You don't have just two sound velocities that control the expansion of these initial densities. You have a lot of possible velocities for all of these modes, all possible momenta. They all conserve, they all have their own propagation velocities, and they make some kind of blurb, something that is a bit much smoother because of the combination of all these velocities together. That kind of explains the experiment. In fact, describes very precisely numerically the experiment. So I've done my 1 hour. So I wonder if I can explain a bit more where this effective velocity comes from, and then maybe I'll stop there. Would that be okay, or should I come to conclusion?
Sure. You can take 10 more minutes, Benjamin.
Yeah. Okay, no problem. So the crucial point in this whole thing is this effective velocity, well, the current and the set of velocities, that describe how each of these theta modes propagate within the fluid. So these are fluid modes essentially with all their velocities. So where does that come from? In fact, this expression, actually, to be honest, so we derived that in quantum models. It was the first derivation in quantum models. We derived in quantum field theory. The other team didn't quite derive it, but kind of had an intuition for where it comes from in quantum spin chains and checked it numerically, and it was very. But in fact, this form, not exactly written like that, but very similar, appeared before us, in fact, much before us, in various contexts. One context is the hard rod gas. So this hard rod gas has been studied in the 80s. And the GEG equation for the hard rod gas was written, proven even mathematically in 82. We didn't know that at that time. We realized afterwards. And so there was an effective velocity there in the hard rod gas. And also in something called soliton gases. This had also been written. And also we were not aware of that. And we realized afterwards. But these are all classical systems. Same structure. So there's also an effective velocity. And so we derived it in various ways, but really the classical understanding of that equation is the best. We realize this afterwards. Take the hard rod gas indeed. So the hard rod gas, what is this? Well, okay, you have particles that hit each other, exchange momentum, and then continue their path. Now the particle exchange momentum, fine, but what we are looking for this rho of theta, we are looking for where the momentum theta is. So we want to follow this momentum theta as it goes along in this gas. So what we want to follow is the velocity tracer. So we start with the particle, say that has some velocity theta, then it hits some other particle, it exchanges it, so it gets some other velocity, which is that of the other particle, but its own velocity now has jumped, so to speak, to the other particle. So if you want to follow the velocity tracer, you have to jump from particle to particle. And now the main point is very, very simple, is that the effective velocity is just the path that this velocity tracer takes within the gas. So this is the combination of the linear motion and the jumps. In the hard rod scattering, the jump is by an amount, by our convention of -a, because it's forward is the negative sign, some convention, doesn't matter too much. It's kind of natural convention for quantum models where usually the jump is kind of backward. But in any case, phi is -a. And so the effective velocity would be that, where you put a constant term there, -a. So it's kind of a bit simpler. In general, well, the jump might not be constant. So if you imagine an integrable system in a two-body scattering, what happened in general, where your two particles, this is a classical point of view, your two particles interact and essentially exchange momenta. It's the only thing they can do because the set of momenta has to be preserved. They exchange the momenta, but there can be a bit of a shift. And here, for instance, it is a shift with a positive phi, where the continuation is kind of a bit, so the jump has been backward. Okay. And the accumulation of all these shifts, these space shifts, or if it's equivalently these time delays, is also is what give rise to effective velocities. These time delays or space shifts can in general be theta alpha dependent, so dependent on the velocities. And the equation for effective velocity is just the combination of that. So there's the bare velocity representing the straight bits of the motion. And then there's the accumulated set of all possible shifts. So the quantity of the shift and integration over all possible particles that can be intercepted, that can be collided with in the gas, with their density and with the probability that you actually collide with such a particle, which is different to velocities. If the particles have the same velocity, you never collide, but if they are different, then you collide. And this is it, that's the equation. And once you have this equation, then you have this. So that equation, yeah, go ahead.
So is this equation local in real space? This equation?
No. So yeah, this is a really a picture, really. Is it? Of course, in reality, you take an actual integrable system with particles, even classical, you cannot separate out individual two-body scattering events. And so this is not a derivation, let's say, okay? So it's just a posteriori explanation, because it doesn't happen, except for the hard rod, it doesn't actually happen like that. But it turns out that this picture is sufficient to explain the equation. Now, the equation we obtained then, we obtained it by saying, using crossing symmetry. Using crossing symmetry, you can exchange space and time. And so you can write the average of the currents by exchanging space and time as average of the densities. Okay? And the average of the densities were already known in integral models by the TBA. And that's how we originally derived that equation. Okay? We just use crossing in quantum field theory. So, and the thetas were the rapidity. There's a plus I pi over 2. Crossing it gives you a rotation by I pi over 2. And we obtained that equation. And a posteriori, we observed that you have that explanation for that equation. So as if it was happening by separate, locally in space-time by separate two-body scattering. although it is not. So I don't know, right? There's no clear explanation for why this actually works so well. My understanding is that, well, it probably works so well because this is an Euler scale equation. It's very large scale. So probably then at these large scales, you can apply this concept that scattering can be separated into a set of two-body scattering at these large scale. And then you can just use this two-body scattering in order to describe the shift that you would obtain in following a certain momentum. So this is really because you look at large scales and you just look at Euler scale, you just get an Euler scale equation. It doesn't happen like that macroscopically. Yeah?
Yeah, thank you. Yeah, thank you.
So this is an excellent point. I mean, this is actually non-trivial. It's a posteriori, if you wish. In any case, then you obtain that, and these equations were already written rigorously shown for the hard rod. Of course, there you can actually separate into two-body scattering, so it's much simpler. But they were also already written in the solitone gas business, where they were derived by using inverse scattering method from classical inverse scattering method. So again, in a completely different way, technical way. I don't think it's completely rigorous, but technical, derivation, you get the same equation. Yeah. So okay, now okay, so so this is a very general structure. I want to say, so all you have to know is the spectral set, the set of possible asymptotic states, the two-body scattering phase, the energy function, and then you can write everything. You can just write your GG equations. It's not a derivation, never, but you can just write it and then check if it works. And it works in many models. It kind of works all the time. The other thing, well, I told you about TBA. There's also another set of integral equation that allows you from these W of theta to evaluate the rows. You have to solve an integral equation, nonlinear integral equation, and then calculate the free energy for that, and then obtain the rows by differentiation of free energy. And it's interesting in this general structure that you have here an additional ingredient, which is the statistics of the quasi-particles. So there may be fermions, boson, classical, or kind of phonons, radiative modes. And so you were asking about the fermions and bosons. So in fact, here in the thermodynamics, in the relation between the W's and the rows, there's the statistic that enters. But in the GG equation itself, no statistics, I'm sorry, that one, no statistics enters. It doesn't matter the statistics. It looks like a completely classical equation. You forget about quantum in this equation completely. Just for that equation, you don't need the quantum. For relating the W to the temperatures to the density, there you need quantum. Like you need to know if it's Bose-Einstein distribution or Fermi-Dirac, right? Okay, so and once you have that, then you can also add a force term. This is how we describe the experiment. So that's all I wanted to say. I mean, there's a lot of application. If you ask me about application, I can tell you. So I want to just say in conclusion that a lot has been done. So a lot of models have been looked at and they seem to work like that. Numerical checks and some experimental checks. There's a lot of structure in these GG equations itself. The GG equations are integrable. There's a MATLAB package has been written to solve them, and there's a lot of stuff that can be calculated, like correlation functions, like fluctuations. And there are some open questions, still many open questions, which I leave there. And thank you for your attention.
Thank you, Benjamin. It was a great talk. It was thanks for the introduction.
So thanks for the question as well. I really appreciate the question to orient the talk.
Okay, let's have more questions.
I mean, this is a very naive thing. In some sense, this theta can be thought of as a bookkeeping parameter, which collects all the conservation laws, right?
Yeah.
So that's what you're doing, right?
Yeah.
Okay.
Yeah. So it's a bit delicate, because the original thinking was to think like you were saying at the beginning. Let's look at all the local conservation laws, right? So the Q there's the energy, the momentum, the particle. Then there's higher conservation law, some kind of energy square or whatever. So things that go like momentum square and cube and force and all that, which you can write explicitly in some model, but in Liebniger you don't know how to write that. So the original thinking was that, but then of course the equations are absolutely useless. And then when you write all this in terms of TBA, thermodynamic beta-ansatz, which is standard technique to write these densities, you realize that you actually don't need all these local conservation laws. And it's much better to think in terms of thetas. So somehow it's kind of, it's a bookkeeping device. So you don't want to know each individual conservation laws, you want a function of theta. Once you start thinking about that, then it's much better. And then what we now realize is that everything is very smooth in theta. So it's kind of the right bookkeeping parameter. So you shouldn't think in terms of conservation laws and what is the right conservation law, the third or fourth or sixth one. It's not quite the right thinking. What you should think of is how the particles are distributed within the theta space, and they're usually nice smooth functions. And these functions change as you evolve in space-time. So basically you should look at the phase space. So x theta. So you really have something like that. You have the x theta space. It's a phase space. And then you have some density plot, if you wish. There's some region where you have particles, and there's more particle there and less there, and all that. And now that moves in space-time. It changes its shape. It kind of changes like shape like that. Maybe it rotates or things like that, right? Moves in space-time. And it's this motion in space-time that GG describes. So actually, the correct description is the motion of a phase space distribution in time. That's correct. So it's really like a two-dimensional fluids. Theta is like an additional dimension. Yeah.
Yeah. So actually, I have a question regarding this picture that you drew, because it is something related to what I think many people are also asking. So if you have this kind of a blob in phase space, the volume will not change, but is there possibility of describing that they like topologically like disconnect? Like
yes.
Then
yeah, this is a very interesting question, actually. So I don't know all the possibilities. There is, of course, a volume conservation. You're perfectly right. There's an appropriate volume element that is conserved. I don't know all the possibilities. Certainly, there is a possibility of these blobs separate. I know one type of possibility. So if you look at zero entropy state, so there's the notion of entropy now that you can go to zero entropy, so zero temperature. In the fermionic system, that means that the mode theta is either occupied or not. It's kind of zero entropy, so you don't have any fluctuations anymore. So occupied or not, that means if you look at the occupation, there's a function n that I introduced, so it's not quite, rho is not quite the right function for occupation. And maybe I just to tell you, just to show you the equation, there is a so-called occupation function, which is just determined by rho. You have another state density and all that, and that satisfies kind of an Arthur equation where the VF is outside. So this in zero entropy state takes value 0 or 1. So let me consider that, and that will exactly connect with your question. So this is n of x. Suppose I start with the usual thermal state with some, this is theta, n of theta, with some free energy there, minus theta f and theta f. Okay. So all modes between minus theta f are occupied, and otherwise they're not occupied. So here is 1. Okay. And this is a fermionic picture. It's actually a correct picture in the Lieb-Diniger model because the emergent degrees of freedom are essentially fermionic. So in many integral models, that's a picture that occurs. So you have occupied and not occupied. Now, what happens when you time evolve, where the earlier equation preserves the entropy? So you stay in the zero entropy state. So things are still 0 or 1, occupied or not occupied. Okay? So what happens? Well, these theta f start to move around. So now you have something like that, and now you have something like that. It starts to move around a little bit. Now, this motion around the theta f actually is very few degrees of freedom. It's just 2 endpoints that move around. So actually, this is back to conventional hydrodynamics. It's just 2 degrees of freedom. But sometimes what can happen is that this C, this Fermi C, can split. And then you have something that people call the Moses effect, or C, where the C is being split in 2 Cs. So after some time now, you can have a topological change where you have more than 2 Fermi velocities. You have, say, 4 of them. So theta 1, theta 2, theta 3, theta 4. And now these start moving around. And then eventually, also after a larger time, these also can split and all that. So you can have a change of topological structures. I think at 0 entropy. So that we have observed. At higher entropy, so I mean, this is essentially what you described. If you look in the x theta space, 0 entropy means that you have a blob which is all 1, fully filled in, everything else is 0. That moves around and eventually it splits kind of in 2 blobs, let's say. And so it's change of topological change. And these changes, it's interesting because so at 0 entropy, if you start with that, what you have, because you have just 2 degrees of freedom, you don't see all the conserved charge. You see almost nothing. In fact, all you see is the first two conserved charges. So this is back to density of particle and momentum. So this is the first question that I wrote. This is conventional hydrodynamics. And in conventional hydrodynamics, what often happens is that when you evolve a wave, you have a wave like that, you evolve it, it may move around, say, eventually it will form a shock. That's typical conventional hydrodynamics. At large time, a big wave would evolve, and then the upper bit kind of moves faster than the lower bit, eventually you form a shock. Now, when you have shock in conventional hydro, you need to add viscosity, and then there's a shock structure that propagates and all that. But here, these shocks, what they give rise to is this separation of this change of topology. So shocks correspond to change of topology. The change of topology is allowed because you have higher conserved charges, you have a high space of states, and the change of topology kind of brings you to a higher space of states. So it's as if geometrically you have this big manifold, and the boundary is the zero temperature, is that conventional hydro where you just have 2 degrees of freedom. But this is high dimensional. So this is the boundary of a boundary, let's say. Then when you go to the more degrees of freedom after the shock, you get to inside that, you get away from that boundary of the boundary, you get inside just the boundary of the manifold. And then, so you have, it's a very high dimensional manifold. You can always get to more and more and more and more. And then eventually you get to the inside of the manifold where you have a smooth function over a phase space. But yeah, okay, so that's an example where you have change of topology in this phase space.
Oh, okay, thanks a lot. Yeah, so is there a possibility that some kind of turbulence might emerge out of this rapid change?
Yeah, so thank you. So you ask all excellent questions. Thank you. I'm very impressed. Yeah, so this is something that has not been analyzed yet, and that I am hoping to analyze in near future. So to apply for a grant and see if we can look at that. So now because of this iFluid package has been written recently, we have access now to good numerics to evolve these equations. Previously, we had some numerics. We have seen various things happening. We have seen like blobs becoming more and more kind of developing these very small structures, kind of filaments developing and all that. But we never had enough precision to go beyond that. And now we have the numerical tool, so I think we can start analyzing turbulence, because it's a bit like a 2D fluid. Yeah, and that should be interesting.
Okay, that's very nice. Yeah, wonderful. And actually, we were also thinking about some holographic analogs of such things, because
yes,
yeah,
yes.
because if you know that there is this co-adjoint orbit of the Virasoro group, it also has, and some of these things holographically represented by some kind of disconnected parts like this. It looks something like that.
Yes, I see.
It's not usually studied, but there are these examples which kind of exotic and indeed. So my initial question was whether this fix can fit into a generalized hydrodynamic story, and it looks like indeed there is a possibility.
Yeah, probably, yeah. So yeah, that would be interesting actually. So I know there is some work. I don't know as much about it. There's some work for describing holographically integrable systems where you have to go beyond the standard things, not that. And surely, yeah. So I'd be interested to see what if you can get to understanding of this kind of stuff, and yeah. What else you can do?
I have seen similar things in matrix models, in one-dimensional matrix models.
I see.
And there's this Darcy-Evicki collective field formulation of that. So there is this droplet model in phase space, and kind of topology change, etc. All these things people have looked in that context.
I see. Interesting. Yeah. So I don't know about it. I have to look into that. Yes.
Yeah. So there's a lot of work in that direction.
Yeah. Okay.
From the from the 90s.
Yeah, and if you know a good reference, maybe you can send me.
Sure, I will.
Thanks. Yeah.
The matrix models have some very similar characteristics, but probably some differences too.
Yeah, no, but the thing is that you think of the eigenvalues as particles moving in some space,
and
then it sort of starts mapping to what he's doing. So some of the techniques wise, I think it's the same, but.
So in fact, it's very good. Yeah, so in fact, there's some connection that's been done by Herbert Spohn on this direction. He looked at the TODA model, which is an integrable model, many particle integral models, and looked at indeed the TBA and GG and all that. And indeed, the thetas of TBA, they are rather simply related to the spectrum of a matrix involved in the Lax pair, so basically Lax matrix. And it is the density in this space of the spectrum of Lax matrix that moves with the hydrodynamics. Yes, it's exactly that. And he was making a connection with some, I mean, his big thing was to make a connection with some result in random matrix theory where he could almost show how the TBA structure emerges directly in the Toda model, the classical Toda model. Mm-hmm. But yeah, there is this connection. Okay, that's very interesting. Yeah, so I should look into that indeed. Show this connection. Yes. Mm-hmm.
Thank you very much.
Questions?
Thanks. Thanks. Okay, I have just one question about higher dimensions. Do you think it can be extended, for example, to describe a gas of anions where even the statistics can change?
Yes, yeah. So certainly. So okay. So already in 1D, there's various statistics that can be used. One can consider, I mean, not higher D anions, but something similar. You know, these free energy functions that you have, you can have in general arbitrary free energy function. And there's a notion of kind of anions in 1D where you can fill in the states up to a certain number n instead of being 1 or infinity, 1 for fermion, infinity for bosons. It can be a certain number n. And then you just have to change this free energy function, which encodes the statistics. And in principle, you have a TBA. Well, I'm not sure how much this has been derived, but. And in higher D, of course, the difference is that you don't have in general the scattering structure, the fact that you have preservation of momentum in and out, unless the model is free. And then if the model is a free particle model, all this applies in higher D without any problem with higher D kind of integrations and all that. But it doesn't tell you a lot because anyway it's a free theory, right? So you can do other techniques. But in principle, still all this applies. You can formally write it and it's correct. But yeah, so if you have interaction, then the scattering structure is different. So I'm not sure if this bookkeeping is the correct one in higher D integral models. That's the question that I would have. I'm not sure what's the correct bookkeeping, let's say. There are some models that we've thought about in higher D where that might be the correct one now that we still have to look into that.
Yeah, but this free energy is a single particle free energy, right? This is,
yes, a single. So in these integral models, basically, you just need 2 particle scattering, single particle free energy, and then you mix that, and you get everything essentially. So you need very little information. That's kind of the power of it. Even for this whole GG, you need very little information. In fact, to get that, you just need to do a 2 particle scattering kind of calculation, which in many cases can be done exactly. It's a simple thing. And you put that in these equations, you have everything. Of course, it's based on the assumption that this is integrable, naturally. And it's a non-trivial assumption, and then that this correct structure is not derived. But just the information that you want is very limited.
Thanks. Yeah. But is there a way to generate? Okay, there are 2 questions that I wanted to ask, 2 simple questions. The first one is that in higher dimensions, you can have this and the different statistics thing fusing and going to something else, for example.
Yes.
The statistics can change. And number 2, you can also have this creation from vacuum.
Exactly. Yes. Exactly. So it's very different. So, and I should say, so this is an interesting question. So all this stuff about kind of that type of construction, asymptotic states, they are perfectly well defined in any dimension, integrable or not. These operators are perfectly well defined in any dimension, integrable or not. So this construction, this operator can be done. It can be written formally. They exist. There's absolutely no problem at all. The non-trivial thing is that for these operators in integral models, there is a local density associated with them and local current, local. And when there is particle production, when there is, the phenomena you talk about, this is what fails my understanding. This is what fails in general. You lose the locality of such operators. In fact, it's absolutely non-trivial. So how do you, it's back to the question that was asked, why can you do this kind of argument, even if it doesn't really happen? Because in integral model, you can almost construct some local object that follow the velocity theta. So this tracer is essentially part of the space of local densities. In fact, it's not quite part of it, but it's like describing a Hilbert space using scattering waves. The scattering states are not part of the Hilbert space; they're not normalizable, yet can be used to describe the state. So it's a bit like that here. So while in non-integral models you don't have that, they cannot be used as a basis to describe all the local things. But why exactly is non-trivial? I mean, I don't fully have an understanding of that. So this is still something to be understood. Yeah.
Any more question, Suresh?
No, I'm done.
Okay, so thanks,
Thank
Benjamin.
you.
Then
thanks. Yeah, thanks for the questions. I think it was a pleasure.
Okay, so thanks also for giving us good time then.
Yes, no problem. Excellent. Yeah, so very nice. So hopefully, yeah, we can meet in the real world at some point. Nice.